Hello, virtual listeners. Thanks a lot for taking the time to tune into this talk. My name is Mitch Bushuk, and I'm a research scientist at the Geophysical Fluid Dynamics Laboratory. And today I'll be speaking about mechanisms of regional Arctic sea ice predictability in two dynamical seasonal forecast systems. Many people have contributed to this work, and I want to say a big thanks to all of my co-authors whose names are listed here. So the primary motivation for this work is the observed decline of Arctic sea ice extent and the corresponding need for skillful predictions of Arctic sea ice on the subseasonal to seasonal to interannual timescale. And so we have three main research questions we're attempting to address today. Firstly, how skillful are current regional predictions of Arctic sea ice? Secondly, what are the key sources of regional sea ice predictability? And third, how do we go about improving sea ice predictions? To address these questions, we're going to use results from two dynamical seasonal prediction systems that were developed at GFDL, the FLOR and SPEAR medium system. FLOR stands for Forecast-Oriented Low Ocean Resolution, and SPEAR is the recently developed seamless system for prediction and Earth system research. You'll see that both of these models are fully coupled dynamical global models consisting of atmosphere, land, ocean, and sea ice components. They have the same nominal resolution of ½ degree in the atmosphere and land components, and use a coarser 1 degree resolution in the ocean and sea ice components. Both systems are initialized using a variety of different oceanic and atmospheric observations. So in both systems, we assimilate satellite sea surface temperatures, ocean temperature and salinity profiles coming from sources such as Argo floats and XBTs, and we do that at daily time frequency. In the atmosphere, we assimilate three-dimensional temperature data from NCEP2 reanalysis at 6-hourly frequency in the FLOR system, and in SPEAR medium, we assimilate three-dimensional temperature, winds, and humidity data from CFSR. Now, neither system assimilates sea ice data directly, but we do incorporate a sea ice concentration data constraint in the SPEAR medium system, in that we use the sea ice concentration observations to adjust the under ice sea surface temperature values. And so you can think of this as a very simplistic way of doing sea ice data assimilation. In terms of data assimilation methods, we use the ensemble Kalman filter in both systems, and SPEAR has an additional nudged atmosphere and SST run, which is used to initialize the sea ice, atmosphere, and land components. And then using these systems, we've ran suites of retrospective seasonal predictions. So these are ensemble forecasts initialized on the first of each month and then run for 1 year of time. And we've done this for the time period spanning 1992 to 2020, which gives us a nice 29-year record to assess the skill of these predictions against observations. So now we can move on to our first science question, which is, do FLOR and SPEAR have sea ice extent prediction skill? As a first look at that, here I'm showing our predictions of Pan-Arctic September sea ice extent. The observed time series is shown in black here, and the predictions made at various lead times, ranging from lead 0, which are September 1st initialized forecasts, back to lead 3, which are June 1st initialized forecasts, are shown in the colored curves. What we see is that both systems have some skill at capturing the observed time series, and we can quantify the skill using the ACC, or anomaly correlation coefficient, and we see values around 0.8 or 0.9 in both systems. Now clearly some of this skill is coming from the ability to capture the downward trend in sea ice, and so a more stringent test is to first detrend both time series and then compute an ACC of the detrended anomalies. And you can see that both systems also have skill for those detrended anomalies, and the skill tends to be higher in the SPEAR system. Okay, so now we're going to move to the regional scale, and we're going to do that by taking the Arctic and breaking it up into these 14 different regions of sea ice variability, and then asking the question, can these systems skillfully predict sea ice extent anomalies in each of these 14 regions? I'll start off with two regions of summer sea ice variability, the Laptev Sea and the East Siberian Sea. What I'm plotting here are detrended anomaly correlation coefficient values for different target months. These are the months that we're trying to predict along the x-axis, and then different forecast lead times going from 0 to 11 months along the y-axis. Anywhere you see a square on these plots indicates that the skill of the system is exceeding that of a basic anomaly persistence forecast, and anywhere you see a dot on the plot indicates that the skill is significant, but it's lower than persistence. The third column shows the difference between the two systems, spear minus FLOR. Anywhere you see an upward triangle indicates that the skill of the spear system is higher than that of FLOR, and anywhere you see a downward triangle indicates the opposite. So we generally see that spear is providing a notable improvement in terms of skill relative to the earlier FLOR system, and that improvement is seen in these regions, especially at lead times of 0 to 3 months. We also see that in both the Laptev and East Siberian Sea, the skill structures tend to have this diagonal correlation structure to them, which is indicative of the spring predictability barrier which exists for Arctic sea ice. Now, the next question we want to address is, what are the key sources of predictability for summer sea ice extent in these systems? And so here I'm showing the detrended anomaly correlation coefficient values for September sea ice extent in the two systems in the Laptev and East Siberian Seas. And what we're going to attempt to do here is reconstruct this skill using a combination of very simple linear regression-based prediction models. We tried a number of different predictors, and we ultimately found that a combination of regional sea ice extent and regional sea ice volume was able to reproduce essentially all of the skill that we were finding in the dynamical models. These predictors are based on the initial conditions that each system used for its forecasts. So here in black, I'm showing the skill of the regional sea ice extent-based predictor, and we can see that at short lead times, we can explain most of the skill of the dynamical model based on sea ice extent persistence, but at longer lead times, the sea ice extent predictor does not do as well. And it's sea ice volume that comes in and provides the dominant source of predictability at lead times of 2 and 3 months. So what we're seeing here is that there's a combination of two predictability sources, sea ice extent at short lead times and sea ice volume at longer lead times, which can explain essentially all of the skill of the dynamical models in these regions. And we also see that we can explain the skill differences between spear medium and FLOR via these linear regression-based models, in that we can see that spear's sea ice extent-based prediction is much more skillful than FLOR's, indicative of improved sea ice extent initial conditions in this system. And we can also see that spear's sea ice volume-based prediction is also much more skillful than FLOR's, indicative of improved sea ice thickness initial conditions in this system. So the paper contains a more comprehensive analysis of other regions of summer sea ice variability, but in the interest of time, I'm going to move on to some regions of winter sea ice variability here and focus in on the Barents Sea and the Labrador Sea. The first thing you'll notice is that these winter sea ice predictions are much more skillful than what we were seeing for summer sea ice. And we think the reason for that is that winter sea ice is simply more predictable inherently. And that's due to its strong coupling with the oceanic conditions in the subpolar seas and the fact that those oceanic conditions are themselves fundamentally predictable. Again, we see that the spear medium system is generally providing improvements relative to FLOR at short lead times. And in the Barents Sea at longer lead times, there's not much difference in skill between the two systems. In the Labrador Sea, we see that the spear system is providing an improvement in terms of its predictions of winter and spring sea ice extent conditions. And then one thing to note here is that you see a mix of squares and dots on these plots, which indicates that while these systems do often have skill at longer lead times, the skill of the system is actually losing to that of a basic persistence forecast. So this suggests that there's a lot of room for improvement still in these systems. So now we can play the same game we played before and ask the question, what are the key sources of predictability for winter sea ice extent in these systems? So here the blue curves show detrended anomaly correlation coefficient values in the Barents and Labrador Seas. And again, we're going to construct a series of linear regression-based predictors in order to attempt to explain the skill of the dynamical models. The black line here shows the skill of the sea ice extent-based predictor, and we can see that sea ice extent does a very good job of explaining the skill of the dynamical model at short lead times. It doesn't do as well at intermediate lead times, and then interestingly at long lead times, we can see that the extent-based predictor is actually beating that of the dynamical model, which is what we saw in the previous slide, where we were actually losing to the persistence forecast in some of these long lead prediction cases. We find that a second predictor, based on the upper ocean heat content averaged over the upper 200 meters of the ocean, does a very good job at sort of filling in the skill over these intervening summer months. And so what this shows us is that this combination of sea ice extent-based persistence combined with upper ocean heat content-based persistence is able to provide quite a skillful prediction of sea ice extent in these regions. And the combination of these predictors, interestingly, is able to generally beat the skill of the dynamical models, which suggests that there's quite a bit of room for improvement in these systems in order to catch up to the skill of these simple linear regression models. Okay, so the final region I want to highlight is our prediction skill for the Chukchi Sea. And what we see in both systems is that there's an interesting skill structure in the Chukchi Sea, where we see relatively low skill in August, September, and October, but then those months are flanked by higher skill values in November, July, and June. So in order to explain this interesting skill structure, we can again turn to an analysis of the sources of sea ice extent prediction skill in this region. And again, I'm going to consider the three predictors based on sea ice extent, sea ice volume, and upper ocean heat content. In the months of June and July, we see that the ocean heat content-based predictor, shown in magenta here, does a very good job of reconstructing essentially all of the model's skill. So this result suggests that the key source of predictability in June and July is coming from the ocean. Now, as we move into August, September, and October, you can see that interestingly, the skill of that ocean heat content-based predictor crashes down to a value very close to 0. And that's the case in both FLOR and SPEAR medium. And the skill is low in August, low in September, and it bounces up a bit in October, but it's still fairly low. And what we see is that over these months, it's the sea ice volume-based predictor that jumps up and provides more skill in this region. And so in these months, it seems to be, again, the combination of sea ice extent in black and sea ice volume in red that's providing the dominant sources of predictability. So we're back into more of an ice thickness-based predictability regime over these months surrounding the summer minimum sea ice extent. And then finally in November, we see that the ocean heat content predictor jumps up rather abruptly and provides skill all the way back to 11 months in advance. So it seems that in November, we're again returning back to this ocean-based predictability regime. And now the natural question is, why is there this trade-off that occurs between ocean-based and thickness-based predictability regimes? So to get at that question, in colors here, I'm plotting the ocean surface current speeds from the SPEAR medium initial conditions. And what we see is that there's an inflow of ocean waters through the Bering Strait. The inflow travels partially eastward along the coast of Alaska, forming the Alaskan coastal current, and it splits into a second branch that flows westward towards Wrangel Island. Now the gray curves on here show the observed position of the sea ice edge in different months of the year. And what we find is that in the months of June and July, the sea ice edge is positioned such that it interacts directly with those warm inflowing ocean waters from the Bering Strait. And as such, the ocean is able to impart a direct influence onto the sea ice. In the months of August, September, and October, the ice edge has retreated sufficiently far northward that the ocean waters come in, curve to the right, and they are not able to actually interact with the sea ice edge. And then finally in November, the ice edge grows southward, and the ocean waters are again able to interact with the sea ice and impart predictability onto it. So it's this combination between the geometry of the inflow and then the position of the sea ice edge in different months of the year that determines the sea ice predictability. So just to wrap up, we've shown that SPEAR and FLOR can both skillfully predict pan-Arctic and regional sea ice extent 2 to 11 months in advance, depending on the region and the season of interest. We've found that the SPEAR skill is generally higher than FLOR's due to improved sea ice extent and sea ice volume initial conditions. And we found that a combination of regional predictors coming from sea ice extent, sea ice volume, and upper ocean heat content can match, or in some cases exceed, the skill of the dynamical models. And we therefore advocate using these 3 simple statistical predictors as benchmark tests for evaluating Arctic seasonal prediction systems. And finally, we found that the Chukchi Sea exhibited this interesting combined predictability regime associated with interactions between the sea ice edge position and inflowing ocean waters through Bering Strait. So thanks a lot for your attention, and I'm looking forward to seeing you at the Q&A session. If you're interested in more details of this study, the paper was recently published in Journal of Climate as an early online release, and the reference is there. Great, so we'll see you all in a few weeks.